Eulers method. And so let's talk about that. So up to this point, nearly every differential equation that you have been presented with has been solvable. This is the exception to the rule, because the majority of the first order differential equations usually can't be solved. So what do we do with the first order differential equations we can't solve? If you want to know the long-term behavior of a solution, you can use a slope field. Okay, and if you want to determine how a specific solution behaves, including some values that the solutions will take, then we can use a numerical method to approximate solutions to differential equations, and this is Euler's method. Euler's method is a numerical approach to approximate the particular solution of the differential equation y prime equals some function of x and y that passes through an initial point. So this would be the point of tangency right here. Okay, so here's how it works. Let me move it up here so you can see it. Okay, so here's the initial point right here. We have our tangent line, our initial tangent line. So from the given information, you know that the graph of the solution passes through this point and has a slope of some function of x and y right there. So the slope of that line at that point. From this point, we're going to move along. So here's how Euler methods work. So what they do is from here, on this tangent line, we're going to move along to a new point, which we call x1, y1, and it is x0 plus some h value, and then h times f of x to give you up to this new y value right here. The old y value plus this change. Okay, and then we can take from this point right here, we can create a new tangent line. Okay, it's not really tangent at this point, but it's another line. And what's happening is I repeat this process, okay, as many times as I want. What I'm doing is I'm literally redirecting our tangent line to follow the solution curve. So here's the original tangent line, and if I kept on going, the farther out I go, the less accurate it is to the curve. So what we do is at a new point, we redirect the tangent line, and what it does is it more closely follows the curve structure itself. And you can do this as many times, and what it is you're just following the curve as to give you a better approximation. The smaller value of h that you use in your for this, then the better your approximation is going to be. So remember, Euler's method is simply a redirection of these tangents, okay, from the tangent line, a redirection to get us closer to the curve as we move around to different solutions. So let's see how this works in reality. So we'll do a problems here together. I have one of our first ones right here. So we're going to let f of x be the solution to the differential equation dy dx equals 2 x minus y. I know it's kind of hard to see here, so I'm going to zoom in and get a better focus here. So this is 2x minus y with the initial condition f of 0 is 1. What is the approximation for f of 2 if Euler's method is used starting at 0 with 4 equal sized steps? Okay, so the process we want to follow here in answering this question is we got to first figure out what is our steps. How big is our steps to make this happen? 4 equal steps going from 0 to 2. And we do this by finding what we call it delta x, or change in the x values, otherwise known as the h in that picture I showed you before. And it is simply b minus a over n, the number of subintervals we wanted. And so this gives us 2 minus 0 over 4, or 1/2. So we're going to do steps of 1/2. And the best way to do this, to keep everything organized, is to make a table. Okay, so here's the table I would make, and it's fairly large depending on how many subintervals you have. And what we do is you're going to have, here's your x, here's a y for the points. Then after that, we want to find dy dx. We're going to take the derivative and find them at these points over here. We're going to use and find a new slope for ever-changing lines as we move around the curve. Once we have that, then we're going to write that new line equation. So we have our point. We find the slope of this line using that point. Then we find a new point, and then we're going to write the equation of that line based off of this new point and a new slope. So we're going to use the derivative of the curve at this point right here to get a new slope. And then we write the equation of that line. Then we're going to use the line to find a new y value. So that's kind of what we're doing here. So here's the line we're going to find. And then over here we need a new y value. And then we just repeat that process as we move along. So we're going to start at the point 0, 1. And we're going to change 1/2 for the x each time. So what I would do is just come down here and make a new column here. This is you're going to add the change of x. So this is going to be 0 plus 1/2. This will be 1/2 is our new. And then we're going to add another 1/2. So the next one down would be 1. And then the next one down would be 3/2. And then finally the last one down here, which is what we're going to be trying to shoot for, is what happens when x is 2. So we're going to be looking for this number right here in our process. Okay? So whatever we get here, f of 2 will be approximately equal to whatever that number is that we get right there. So here's our process. Here we go. Here's our derivative, 2x minus y. Here's my x, here's my y. We've got to find the slope of that. So we simply plug in 2 times x minus y. We get -1. So using this point and that slope, we're going to write the equation of a line. So y1 is going to be the y value minus slope times, and so this becomes x minus 0. And then what we're going to do now to get a new y is we're going to take this value, this y value, this equation, and we're going to plug in 1/2, the new x. So we plug that number into this line we just created, and we get a new y from that. And we get 1/2, and so that number now goes here. So this is your new y point. And we just repeat this process. Take these two numbers and plug it into the derivative, and get a new answer, which is 1/2. Write a new equation. This is now y2. We need the y value, and then we're going to have the slope, x minus the x value, and then we're going to plug in the next x into that equation, and we get our new y value for the next line. And you work this out and you should get 3/4. So that means that number comes over here. So this is the process that we're just going to use over and over and over again. Okay? And you just keep on going until you get to the 2 value that you're looking for. So this would be 2 times x minus the y. This is 5/4. Now we're going to do a new y value, a new line. So it's the y value plus the slope, x minus the x value. And then we take that line and plug in the next x value into it to find the new y one from this point forward. So we have 3/4, 5/4, 3/2, minus 1. And you can work all this out and you should get 11/8. And there we go, last round. So now we do it again. And then we have minus 11/8. You work this out, you'll get 13/8. Here's my new one. 11/8. 13/8. X minus 3/2. And then we're going to plug in what? Now you plug in 2. 11/8. 13/8. 2 minus 3/2. And then you work this out and you're going to get 35/16. 35/16. So our approximation is 35/16. And that's the Euler method. Okay? Hopefully you won't have to do too many iterations to get to your answer, but that's how it's done. Okay? So let's look again at another one. And we'll just do more examples on how these might appear on your AP exam. Here we have a function y is f of x, be the solution to the differential equation dy dx equals f prime of x. With the initial condition f of 1 equals 3. Selected values of f prime are given in the table, which I forgot to write, so I will write it for you here in a second. What is the approximation for f of 1.6 if Eulers' method is used starting at 1 with 3 equal subintervals? Here is the table I forgot to write. So here's x, here's f prime of x. So at 1.0, 1.2, 1.4, 1.6, 1.8. This is 2, 2.3, 2.5, 2.7, and 2.8. So there's our table. So we want to find our change in x. So just like before, our change in x is going to be the b minus a over n, which in this case will be 3. Our b value is 1.6, our start value is 1, and our iterations is we want 3 of them. So when you work this all out, you're going to get 0.2. So that's our change in our x's. And f of 1 is 3. So we make our table. Here's my x, that's my y, that's my dy dx. This is my line, and this is my new y value. Okay? So I'm going to start at 1, and y is 3, and then I'm going to do changes of 0.2, so this will be 1.2, and then 1.4, and then 1.6 is where I'm going to end. Okay? So our slope is f prime. Here's my numbers for f prime. So we need to plug in f prime at, when x is 1, our f prime is going to be a 2. So that means this slope is going to be 2 at 1. So we write our equation of our line. So our y1 is going to be 3 plus the slope times x minus 1. And then we're going to plug in the next x value, and we get our next y value. And when you plug this all in here, you're going to get 3.4. 3.4. And then we do it again. What is the derivative at 1.2? At 1.2, it's 2.3. And so y2 is going to be the y value, 3.4, 2.3, x minus 1.2, and then plug in the next value. And so in doing this, here's 3.4, 2.3, 1.2, sorry, 1.4 minus 1.2, and then when you work this out, you're going to get 3.86. And you can check all my numbers with your calculators just to make sure I'm doing it right. If I have an error in here, just correct it on your paper. At 1.4, the slope is 2.5. And so we just keep on going until we get to the value that we're looking for. And plus 2.5, x minus 1.4. And then this will get us our final answer here at 1.6. 3.86, 2.5, 1.6 minus 1.4, and this will give us 4.36. So 4.36. And then here's how you want to write it. F of 1.6 is approximately 4.36. Don't leave it like this, write it like that. Okay, that's what they're going to be looking for, and that's answering their question. Okay, so that's the techniques there. I have some other ones that come about. Here's one for you to try. Okay, so y is a solution to the differential equation dy dx equals x times y plus 1 with the initial condition of f of 2 is equal to 1. What is the approximation of f of 1 using Eulers' method with two steps of equal size starting at 2? So take a pause here and see if you can figure this out on your own using the process I just showed you. And go ahead and pause it, and then I'll do it myself. Okay, so hopefully you have yours, and so here we go. Same thing as always, we want to find our step process here that we're going to use. This is going to be the b minus a. So in this case, we're starting at 2 and going back to 1. Okay, so that means our end value is 1, our start value was 2, and we're going 2 steps of equal size. And so this gives me a step size of negative 1/2. Okay, and so then when I make my table, here's x, here's y, dy dx, the line, the new y. I'm going to start at 2 and 1, and then I'm going to go to the next line. I'm going to subtract 1/2. So this is now going to be 1.5 or 3 over 2. I'll leave it as a fraction. 3 over 2, and then one more step, negative 1/2, and so this is going to become the 1 right here. Okay, so here's my x times y plus 1, so 2 times 1 plus 1, so y equals 1 plus 3 times x minus 2, and then y of 3/2, 1 plus 3 times 3/2 minus 2 gives me negative 1/2. Okay, 3 over 2, negative 1/2 plus 1 gives me 1/4. And this is going to be a negative 1/2 plus 1/4 x minus 3 over 2. And so then at 1, what do I end up with? Negative 1/2, 1/4, 1 minus 3 over 2, negative 5/8. Negative 5/8. So f of 1 is approximately a negative 5/8. Just like that. And you have to write that. You have to write this statement. This is what they're looking for when you do Euler method. So make sure that you do indeed write it. So what about something that looks like this? Here is f of x. It looks like that. X is greater than 0. F of x is the length of the graph of g from 0 to x. Use Euler's method starting at 0 with 2 steps of equal size to approximate f of 2. Okay, so this process here, we got to figure out all the stuff that we're normally going to do. The first one is, what is my change in x's? Starting at 0, we're going to 2, so it's going to be 2 minus 0. I want 2 steps, so each step is 1. And all the other ones, I gave you the starting value, but this one I did not. So that means we have to use this concept here to find the start value. So what is f of 0? Well, that's integration from 0 to 0 of this quantity. And we know that's going to be 0. The other thing we need to know is we weren't given a derivative here. So what is f prime of x? Well, because this is the fundamental theorem of calculus, if I'm taking the derivative of integration, this quantity right here gets replaced in here for the t, and then times the derivative of that, which would just be 1. So this is just simply going to be the square root of 1 plus 6x squared. So using that knowledge, getting this all set up here, we can now make our table. Here's my line, and here's my new y. So my start value is 0, 0. My steps are going to be plus 1. So this will be 1. And this will be the 2. Okay? And so then my dy dx is this right here. I'm going to plug in this values in here, so I'm going to get the square root of 1 plus 6 times 0 squared, which is simply going to be 1. So y1 is this y plus the slope times x minus 0. And so then what is y at 1? So I'm going to get the 0 plus 1 times 1 minus 0, which is 1. 1. Do it again. This is going to be 1 plus 6 times 1 squared, which is going to be the square root of 7. So y2 is going to be 1 plus the square root of 7 times x minus 1. And so what is y2 at 2? 1 plus the square root of 7, and then it's going to be 2 minus 1. And so this gives me 1 plus the square root of 7, 1 plus the square root of 7. So f of 2 is approximately 1 plus the square root of 7. And there you go. Okay. Last example right here. Little twists on things, and so let's see how it all plays out. Here's y equals f of x, be the solution to the differential equation dy dx equals x times y, with the initial condition of f of 0 is 3k, where k is some non-zero constant. Euler's method is used with two steps of equal size starting at 0 and gives the approximation f of 2 is approximately 1/3. Find the value of k. Alright, so let's go through our process again. Start off, what is my change in x? I'm going to 2, I'm starting at 0, and I want 2 steps. Each step is 1. Okay, I need to know my starting value, which they gave me is 3 times k, and they also gave me my end value, so I know the answer is 1/3, approximately 1/3. So when I set all this up, keep that in mind as we go through this process. So dy dx, there's the line, here's the new y. So I'm starting at 0 and 3k. I'm going to step it by 1 each time. So in here, my derivative is x times y, so this is going to be 0 times 3k, which is 0. So my first line is going to be the start value plus 0 times x minus 0. And so y1 at 1 is simply 3k. So 3k again. So plug it in here. Now we're going to have 1 times 3k. So now we have 3k. And so this is y2 is the start y value, 3k, excuse me, and then plus the slope, which is also 3k, x minus 1. So now what is this when I plug in 2? 3k plus 3k times 2 minus 1 gives me 6k. So what I know from this is this was 1/3, and that is that. So I know that 6k is 1/3. So k is 1/18. And there you go. Okay? So that's Euler method with a lot of different techniques that you might be using on the AP exam. So if you have any questions, let me know.